Alright, in this video I'm going to be talking about pull up and pull down resistors. So, and what do they do? Okay, so just take a look at this circuit I have in front of me right now. Um, and I want you to ask yourself this question. When the switch let's say when the switch is closed. When the switch is closed, can you tell me what the voltage across the load is, or what is the voltage supplied to the load? Um, and then, okay, let me just write like, okay, 9 volts. Let's say the supply is 9 volts. When the switch is closed, can you tell me what is the voltage of L? And when the switch is open, can you tell me what is the voltage at the resistor? So try it out for yourself. Okay, when it's closed, when the switch is closed, the voltage at L is actually going to be 9 volts. It's going to be 9 volts because KVL, right? I mean, not really KVL. You can just think of it as, oh, I mean, it's pretty simple circuit lah. So when the switch is closed, the voltage at L will be 9 volts lah. But what did you say when but what if when it's open? Some of you might say, oh, it might be 0 volts. I think 0 volts makes sense because there's no power being supplied to the resistor. So it has to be 0 volts ma. And to this, I would say you're right to a certain extent. But notice how you're not really supplying 0 volts, like you're not having like another source which is 0 volts. What you're having is just an open point in the circuit. Do you see this? So the difference here between closed and open is when closed, 9 volts is forced to go through the load L because look, it's literally being tied to it. But once you open the switch, there's no like source that is 0, or rather in other words, right, there is no ground. To make something be supplied, why am I not drawing? To supply something with 0 volts, right, you can just ground it. Or in this case, it's not being fully grounded. So who's to say that at this point here, or in the voltage across L, is actually 0 volts when the switch is open? And if you're thinking this way, then you should congratulate yourself because that is what we are going to be talking about here lah. So the voltage in a practical setting will not be 0 volts but would be very, very close to 0 volts. You may have in some cases like negative 0.1 volts or like 0.09 volts or whatever. It's just going to be a very close value to 0 but not 0. So Nikki, what's the point of knowing this? It doesn't really make a difference. Yeah, and then today I'll say, yeah, that is true. There isn't that much of a big difference, but the difference can start to show when you're dealing with very, very delicate or digital circuits. For example, if you have a circuit for counting and then you need to increment a decade counter, this lapse, or not really this lapse, this inaccuracy of not having 0 volts when this switch is open could potentially cause issues in that delicate digital system. As such, right, it is not good lah. One thing to note, right, is that when you have AKA, or no, not AKA, bunny ears voltage are being supplied to a component that's not being tied down, this is known as a floating voltage. It's floating, okay? It's floating. And this is undesirable for delicate systems. Okay, so okay, I guess I know that now, but then wouldn't this, okay, and this is a switching system circuit obviously, so doesn't this switching system have an issue for when the switch is open? Yes, there is. Okay, so how can we solve this? Okay, so what engineers did, right, is that they came up with the pull up resistor circuit and the pull down resistor circuit. And I will talk about how the pull up resistor works first. Okay, so this is the pull up resistor, and to show you how it works, right, I'm going to be talking about when the switch is closed, what's happening in the circuit, when the switch is open, what's happening in the circuit. So let's see when the switch is closed, what happens. Okay, when the switch is closed, current is going to flow through here. Then now the current, right, will be met with a choice. Okay, the current can choose to either go through this switch or the load. You need to know an important fact here. The fact is that electricity follows the path of least resistance. So the switch, there's just a wire, or versus the load, who has the lower resistance. In this case, it is the switch, because there's literally virtually zero resistance. And as such, right, the currents will flow here. And the current will not even bother going through the load. Or if it does, right, the current is going to be very, very, very minuscule, very, very small current. As a result, when the switch is closed, the voltage supplied to load will be pretty much zero, since the current is so small. So that is when the switch is closed. What about when the switch is opened? Okay. When the switch is opened, the current will flow from the source again, and then now it will reach this node, and then we can ask the question, will it go here, will it go here? But look, this is an open circuit, so how can the current flow through here? Oh no, my computer's lagging. Yeah, how can the current go through here? And the answer is no, it can't flow through this way, because it's an open circuit, and then it has to flow through this way. So when the switch is open, current will flow through the load. Yeah, so you may be asking yourself, what's the point of that? Okay, remember what our goal was? Our goal, right, was to have a circuit such that we will never ever have this floating voltage and supplied to the load. And don't you realize we have achieved that? When the switch is closed, as we already have established, the voltage will actually just flow to the load. And when it's open, look, sorry. When the switch is closed, the current will flow all the way to ground, and it's not open, it's not floating, but the load will still receive 0 volts. But when the switch is open, the load will receive 9 volts. So we have just created, or I have just explained, right, a circuit where we can get 0 volts, we can get 9 volts without the need of having this floating error here. Okay, and this is pull up. Next, we're going to talk about pull down. This is pull down. In pull down, pretty much the only change is that the resistor and the switch flips position. Okay, if you want to, I would highly recommend now you pause the video, you reason out how this works. Okay, so let's talk about when the switch is open. When the switch is open, current will flow here, and then current will stop. Because this is an open circuit, so it won't go any further. And then you may be thinking, wait a second, then the load, connected to here floating what? No, you're wrong. Because look, the load is being connected to ground, so it'll be 0 volts. So when the switch is open, the voltage supplied to the load will be 0 volts, exactly 0 volts, because it's connected to ground now. Now what if when the switch is closed? When the switch is closed, now current will flow from the source, reach this node, and then have a choice. So we can follow the same principle. Electricity flows through the path of least resistance. In the case of a pull down and pull up circuit, right, resistor circuit, the resistor here that is added, right, will usually be a very, very, very high resistance, like 10 kilo ohms. In here, it's not really beneficial to have 10 kilo ohms, but in here, it's essential for the resistor to have a very high resistance. And that is because when the switch is closed, we want it such that the resistance here is higher than the resistance at the load, such that the current will flow through the load and not through here, because here will be higher resistance. So when the switch is closed, the voltage supplied to L will be 9 volts. And then again, in both of those states of the switch being open and switch being closed, there is no case where there is floating voltage. Look, when the switch is open, L will be 0 volts due to this ground. So no floating voltage. When the switch is closed, L will be 9 volts or high voltage because of the source. And that's it. No floating voltage, and then we're done. So that is the pull up and pull down resistor circuit. You need to know them. You need to know both. Perhaps one way you can remember which is pull up, which is pull down, is when the switch is open for this one, the load will be high. When the switch is open for this one, the load will be low. So you can imagine the switch open being like in its natural state. So naturally, in the pull up resistor, the voltage across the load will be pulled up to the highest, which is 9 volts. In its natural state, in the pull down resistor circuit, when the switch is open, the load will be pulled down all the way to the lowest, being 0 volts. This is one way you can remember which is pull up, which is pull down. So that's pretty much it for this video. Thanks for watching.